Welcome to our lesson on heat and temperature, fundamental concepts in algebra-based physics. We'll explore how these concepts govern energy transfer and phase changes, crucial for understanding the physical world around us. Temperature scales like Fahrenheit, Celsius, and Kelvin provide distinct ways to measure thermal energy. Fahrenheit uses 32 degrees for water's freezing point and 212 degrees for its boiling point, a 180-degree range. Celsius sets water's freezing point at 0 degrees and boiling point at 100 degrees, a more intuitive 100-degree span. Kelvin, the absolute temperature scale, starts at absolute zero, where all molecular motion ceases, with 0 Kelvin. Converting between these scales is straightforward. Celsius to Fahrenheit is 9 divided by 5. Times temperature in degrees Celsius plus 32, and Fahrenheit to Celsius is Fahrenheit temperature minus 32 times 5 divided by 9. For Kelvin, simply add 273.15 to Celsius, K equals C plus 273.15. This relationship is fundamental in many physics calculations. Energy units are also crucial. 1 calorie is the energy needed to raise 1 gram of water by 1 degree Celsius. To convert joules to calories, remember that 1 calorie equals 4.184 joules. For kilocalories, divide by 1,000. Heat transferred, denoted as Q, is calculated using the equation Q equals mc delta T, where m is mass, c is specific heat, and delta T is the change in temperature. The units for Q are typically joules, derived from mass in kilograms, specific heat in joules per kilogram per Kelvin, and temperature change in Kelvin. It's vital to distinguish between temperature and heat. Temperature measures the average kinetic energy of particles within a substance. Heat, on the other hand, is the energy in transit, flowing from a hotter object to a colder one. Specific heat is the amount of energy required to raise the temperature of 1 unit of mass of a substance by 1 degree Celsius or Kelvin. Latent heat of fusion is the energy needed to change a substance from solid to liquid at its melting point without changing temperature. Latent heat of vaporization is the energy required to change a substance from liquid to gas at its boiling point, also without a temperature change. Heat transfer occurs through 3 primary methods: conduction, convection, and radiation. Conduction involves direct contact, like heat moving from a hot stove burner to a metal pot. Convection is heat transfer through fluid movement, such as boiling water, where hot water rises and cooler water sinks. Radiation is energy transfer via electromagnetic waves, like the warmth you feel from the sun or a campfire. The equation for heat absorbed or transferred, Q equals Jakob's mc delta T, is central to many thermal problems. For calorimetry, where heat is exchanged between objects, we use the principle of conservation of energy. The equation M1C1 plus M2C2 equals 0 states that the total heat exchanged in an isolated system is 0. When a substance undergoes a phase change, the heat transferred is given by Q equals mL, where L is the latent heat of fusion or vaporization. Let's consider a worked example. A 0.5 kilo iron block at 100 degrees Celsius is placed in 2 kilos of water at 20 degrees Celsius. What is the final temperature? Using the calorimetry equation and knowing the specific heats of iron and water, we can solve for the final temperature, Tf. After calculation, the final equilibrium temperature of the system is approximately 22.3 degrees Celsius. For our second example, imagine mixing 100 grams of water at 80 degrees Celsius with 50 grams of water at 10 degrees Celsius in an insulated container. Applying the law of conservation of energy, the heat lost by the hot water equals the heat gained by the cold water. Solving for Tf, we find the final temperature of the mixture to be approximately 56.7 degrees Celsius. Understanding heat and temperature is crucial for many scientific and engineering applications, from climate science to material design. Keep practicing these concepts and equations to master the fascinating world of thermodynamics.